so this is going to be the new setup for these classroom videos because I feel like this is better. For the rock ID videos and traveling videos, I'm not really looking at a screen, so I don't need to constantly look away from the camera to look at my notes. But for the classroom videos, since I do have like a lesson plan and a presentation that I need to follow along with for, to make it easier for the editor for you guys, I kind of do have to look at the screen most of the time, so I think we're just going to be doing this. And if you guys really hate it, let me know. If not, we're good to go. So yeah, in the background you can basically see the other half of my room that you guys usually don't see. I am a painting and poster girly. So anyway, we're just going to go ahead and get right into it. That, aside from the little rambling at the beginning, this video is actually about volcanoes. And if you're anything like me, that you're probably more excited for this video than you have been for most of the others. I'm a volcano and earthquake girl. I know that this sounds a little twisted, but those like natural disaster movies that sometimes like, I feel like they're never as popular as other like action, thriller, horror, stuff like that, but I've always been way more freaked out and way more fascinated by natural disasters than anything having to do with like ghosts or like killers. Honestly, killer movies rank on the bottom 3 for me out of the things that could scare me. Before them are ghosts, and at the top are natural disasters. So, but I also have a love-hate relationship with natural disasters because I'm fascinated by them. It's like black holes, but we're not going to get into that. Anyway, so this video is about volcanoes. I was way more excited to make this video than most of them, honestly. I mean, I'm excited about most topics in geology, but this is right up there. So yeah, I'm going to teach you guys a little bit about it. So today we're going to be covering like all the foundations essentially of how volcanoes work, where they come from, like how they form, and how they work, like why do they erupt the way that they erupt, why are some volcanoes more explosive and violent than others. That's all going to be covered here. So basically today we're going to be going from the foundations of what actually is a volcano, so we all have a basic understanding of what we're actually talking about. Then we're going to talk about magma composition, because that is important. Remember, I think in the igneous video I mentioned that the composition of the magma does actually end up deciding what kinds of volcanoes are created. Well, this is a video that follows up on that comment. So then obviously the third thing we're going to talk about is types of volcanoes, again having to do with magma composition. And then the fourth thing we're going to talk about is the tectonics of volcanoes, basically like how volcanoes form, because aside from the magma movement, they tend to be more active in certain tectonic environments. And that's why you won't see certain volcanoes in some parts of the world, but you'll see them all kind of, not convalescing, like they're all gathering in specific parts of the planet, and there's specific reasons for that. So basically, what is a volcano? So there's 2 different things you guys need to know about for this definition. The first one is the volcanic vent. That's basically the opening through which the lava comes out of. The volcano itself is actually not the vent, it's the buildup of material around the vent. It's like the slopes that you see. That's the volcano, not the actual thing that's opening up into the ground that's letting all the lava come out. Obviously, a lot of you guys might be sitting here like, obviously the volcano is not where the lava comes from, but for some people that may not be as intuitive, especially if you're younger, so just have patience for these explanations. So basically, like I said, volcanoes are built by the accumulation of erupted lava. Via cracks in and beneath the volcano, vents can connect to magma chambers and actually continually erupt over periods of time. That's why some volcanoes erupt many, many, many times. Some volcanoes actually only erupt once. And I'm going to explain that later. But the ones that erupt a lot, it's because the cracks in the volcano are actually connecting to other magma chambers where there's still like a stockpile of hot magma that can still keep coming out. The only way that those volcanoes will stop erupting is if they either lose access to viable magma chambers for any reason, like structural collapse, or if the whole volcano destabilizes and collapses. Like, that tends to leave behind craters where actually some other volcanic activity can start later. There's that. So how does it actually work, though? Remember the whole buoyancy thing that I was talking about how igneous flows and like magma reach the surface? Basically, because the magma is lighter in density than the surrounding rock inside the Earth's surface, like beneath it, that I should say. Because it's actually lighter in density, it tends to float. You know how like how water and oil basically difference in densities. It's the reason that when you put water and oil in like one container, the oil will float on top because it's less dense. So magma acts the same way. Magma is less dense than surrounding rock, so it will float to the top. And then it's just gonna keep floating through all the surrounding material as it gets lighter and lighter and lighter because liquid is less dense than solid until it eventually breaches like certain weak points in the crust and starts erupting. Sometimes magma also settles in a magma chamber if it can't go any further up for any reason. And that can end up causing eruptions later if cracks start kind of getting there that allow it to come up to the surface. So basically, how does eruption actually, happen? So basically, like I said, volcanic vents connect to magma chambers. So how does eruption actually happen though? Like we know how basically what a volcano is. Now we know where magma can come from, all that stuff, but how does the eruption actually happen? So basically, molten rock can pour from vents in very fluid flows, or it can shoot violently into the air as like clouds of little rock particles, and we call that tephra. And gas also erupts out of volcanoes. That's why sometimes the most dangerous in terms of life-threatening volcanoes that exist are not ones that explode violently, but there are certain cracks in volcanoes that can actually emit gases that are very dangerous. And as they flow downward, if there happens to be a population close enough that the gas can reach it, populations can die overnight if they're not aware that this is happening without even knowing that they're in danger just because of the volcanic gases. So keep that in mind if you ever feel like living near a volcano. Maybe rethink that. It's not just the eruptions you have to worry about that kind of announce themselves. Sometimes gases can sneak up on you. So basically, the tephra clouds descend down the volcanic slope due to gravity, with larger pieces falling out and forming more volcanic slope because that's how volcanoes are built. Smaller pieces, which we call ash, can be carried as far as the other side of the world on the wind. And by the way, vents can actually be seen in the vents that the lava comes out of can actually be seen in cone and shield volcanoes. Sometimes it's going to be a little harder to see it in more explosive volcanoes just because of the way that they work for composite volcanoes, but we'll get into all that specification later. So now on slide 6 is actually a picture of tephra. It's basically just a tephra cloud coming out of an active volcano. So basically the shape of the volcano and as well as the type of lava that comes out and how it travels and the eruption style, that's all a result of the composition of the magma inside. So let's look at composition since that leads into the types of volcanoes. Basically, mafic magma do have faster flows. They're less explosive because they're lower in viscosity and they tend to have lower gas content as a result. And the volcanoes tend to be lower to the ground and not very steep-sided. Now, for felsic magmas, you do have slower flows, but believe me, that does not make them less dangerous. All it means is you can probably outrun them. Maybe you have a higher chance of getting away from these flows, just the actual flow itself, versus a mafic flow that you will never in your life be able to outrun unless you already have a huge head start. The problem with felsic magma and felsic volcanoes is that even though the flow is slower, technically, the flow of magma, by the way, not everything else that comes out of these things, despite the slower flows, they are more explosive because they are higher viscosity magmas and they tend to have more gas trapped inside. Volcanoes tend to be taller, they can be very steep-sided, and they can have multiple domes. Now, slide 8. Well, let's get deeper into mafic magmas to understand how these volcanoes are formed. They have a low silica content, mafic magmas that is, less quartz and stuff like that, less things that make up quartz, for example. And they do have higher magnesium and iron inside. The flows are gentler since any gases that might have been trapped in this magma can easily escape once pressure starts loosening up. And it's not really as sticky as felsic magma just because there's not much silica in it. And I'll explain what I mean by sticky once I get to felsic magmas. There are three major like lava categories for like mafic magma, and some of you guys may have heard this. There's pahoehoe, and there's more like pillowy magmas as well. The pillows that you see like what is it, like pillow lava or something like that? Pillow basalts is what I was thinking of. Pillow basalts are just basically the like what you see along like mid-ocean ridges, and it's just basically the pillow itself is a type of lava flow. But anyways, so is thicker than all the others, and it does tend to have like a brittle or thick crust on the surface, because like any fluid, it basically has the top of the fluid and then the inside of the fluid that's flowing, like the bottom, you could call it. The top, as it reaches the surface, tends to start solidifying faster than the rest of the lava flow, and that surface is more brittle or thick for lava. The solid surface below the crust, once the lava cools, tends to be sharp, angular, and jagged. Like once the whole lava flow cools, is what I mean by that. That's when you find like sharp, angular, jagged, like crystallized lava, basically. Pahoehoe is thinner than and it is flowing more readily. They create some really cool structures with it. Like basically really cool structures are created with this magma, or with this lava, that is. I should slow down so I stop stumbling over my words, right? So basically, like I said, the crust is smoother. Like the crust on the top is smoother. It is more wrinkly looking. The lava tends to flow in lobes, so it kind of like in more of like a this sort of thing. Like most, lava flows like this, right? And then Pahoehoe lava kind of flows more like this, kind of getting bigger and bigger as it goes down. And it forms like really twisty, bendy shapes and like cool igneous structures, like lava tubes, for example. And then pillow lava is basically what happens when lava meets water. Like, basically, lava cools really quickly when it meets the water, and it forms rocks that resemble pillows. That's why they're called that. And you tend to see this more like where volcanoes are really close to the ocean. You see it along the coastlines or in mid-ocean ridges, which are basically underwater volcano. And you heard that right, there are underwater volcanoes. A little more about the lava tube, because I have a note here that I don't have in the presentation. So basically, as the outer layer of the lava cools and solidifies, the inner part of the lava flow stays fluid and keeps flowing through these hardening tubes of crust, leaving lava tubes. So there's that. So now let's look at slide 9. That just shows you the two different examples that I was talking about. And Pahoehoe. I hope I'm pronouncing that right. I am not Hawaiian, so yeah, I'm a different kind of islander. So I hope I'm pronouncing that correctly. The one on the left is lava. As you can see, it has like a harder, more brittle looking crust on top that's hardening, while the rest of the lava flow is still pretty hot, so that's why it looks that way, all red and stuff like that. And then there's Pahoehoe lava. As you can see, as it flows out, it just keeps going into those lobes. Yeah, they're pretty cool. I first heard about this in university. I didn't even know that there was different like categories of lava flows. Just another reason that volcanoes are cool. So yeah, then there's slide 10, which shows you some pillow lavas, both underwater and exposed to the surface on the ground. Probably that meant that there was some kind of there was some kind of underwater volcano, or there was at least water somewhere in that area once, even now that it looks very dry. Yeah, again, another note about geologic history, you can find out really cool stuff. For example, this might have been like a very arid area, and they would not have expected water to ever be around, but the presence of pillow lava implies that there must have been water there at some point. So then moving on to slide 11, which is felsic magma. So basically, felsic magma, like I said, flows slower, but it is more explosive due to higher viscosity and gas content. And the reason for this is that it has a higher amount, like percentage of silica and aluminum in the magma, so the magma is stickier. Basically, silica content tends to form like thick, wet, tangled webs of connected atoms and molecules that trap gases inside and also make the flow more resistant. Like, it doesn't flow as easily, it keeps trying to like kind of stop. I don't know if you guys have ever seen molasses flowing, but it's kind of like the difference between molasses and water. So it's very explosive and it has a very violent eruption style just because of the fact that it's so resistant to flow. So like once it finally does erupt, the quick depressurization means that everything tends to kind of fly up, and that's why it's more explosive. So basically, any gases previously trapped under pressure and sticky flows, they do escape pretty explosively. And the more enriched in felsic content that a magma is, like the more felsic it is and further away from intermediate volcanoes, the more explosive it is. It is basically like another example I'm going to give you. Molasses in water was the first example. Another one would be like blowing bubbles through a straw in a milk versus a milkshake. The bubbles pop more violently in the milkshake versus the milk. And now we are moving on to the types of volcanoes that there are. So, like I said, that is determined by magma. This is just basically showing you all the different types of volcanoes in one diagram. Sorry, I was sick. I'm still recovering apparently, so there's that. Anyway, so yeah, those are the 4 different types of volcanoes. There's cinder cones, composite volcanoes, which are also called stratovolcanoes, and then shield volcanoes, and then lava domes. Lava dome is really more a style of like eruption, but I'll explain that later. So yeah, there's like the cinder cone volcanoes are more explosive because they tend to be seen more in composite volcanoes, I believe. No, I think I could be wrong. Let me not get ahead of my notes. So yeah, those are the 4 different types. Just kind of look at them. You're not really going to understand them until you actually hear more about them in detail each, but you can come back to this slide later or to this point in the video. I guess you're not the editor. But yeah, you can go back to this point in the video if you would like, just to look at them once you have a better understanding. And I'll come back here as well to explain certain things, so you don't even have to go back, I will. Anyway, so slide 14. So basically, shield volcanoes are the ones that are composed of mafic low viscosity lava flows. Since lava flows with less resistance, like in mafic magmas, it tends to flow further out. And that makes the volcano bigger in distance than in height. So more felsic volcanoes tend to build up, up, up. On the other hand, shield volcanoes or mafic volcanoes tend to kind of keep building out instead. The lava can basically so the volcanoes are squadron shaped, close to the ground with gentler slopes. The reason that they're called shield volcanoes is because their shape makes people think of a warrior's shield lying close to the ground with like the actual protective part pointing up. Basically, lava runs further distances than in felsic volcano types. That's how come those volcanoes tend to be massive lengthwise. And lava can pour out of vents in all directions, either from the top, which is the summit, like this big hole right here in the center, or from fractures radiating out from the summit. As lava flows intersect, they kind of create a gently sloping dome shape, and that's how they end up looking like that. Basically, these volcanoes build slowly, okay, through thousands of lava flows spreading over wide distances that then cool as like thin sheets of igneous rock nearby. And yeah, so basically an example of that is on slide 15, Mauna Loa. Again, I hope I'm pronouncing that correctly. I probably am not. Like, that's one of the more famous ones. Basically, all of Hawaii is on a string of volcanic islands, and I think at least 2 of them are mafic volcanoes and like, shield volcanoes. And that's why they're the ones who basically named the 2 types of lava flows that are like not more common, but more common above ground, which is the A'a and the Pahoehoe. The pillow lavas can be named by other people because they tend to be more in water contact. So that you actually tend to see them more along mid-ocean ridges than along the coastline, by the way. So yeah, we're moving on now to composite or stratovolcanoes, which are composed of felsic lava, like stickier felsic magmas that pile up higher and higher near the vent. And they're unable, so basically how this works is because felsic magma is stickier and resists flow, it doesn't get very far once it erupts. It just keeps building up and up and up, so the volcanic vent keeps growing longer and longer and longer and longer, pointing up towards the sky, and the volcano keeps building very high up like that because it can't get away before it hardens. The volcanic necks tend to be made of alternating lava flows, tephra, cinders, blocks, and volcanic bombs. Yeah, you have a lot more going on with these volcanoes usually than you do with like more mafic volcanoes. So then now we're on slide 17. Now, slide 17, the pyroclastic flow is one of the things that you tend to see more with felsic volcanoes. This is basically like a rapid avalanche of hot volcanic gas and tephra, which is pumice, ash, rock fragments essentially. Depending on the volcanic slope steepness and the eruption volume, like how much lava is coming out, speeds can reach like 430 miles per hour. That is super fast, okay? You're not going to outrun that. Like, basically, the pyroclastic flow is the most dangerous only because of how fast it can go. Like, it can really mess up an entire group of people before they even realize that the volcano has actually, for real, erupted. Because sometimes volcanoes give you false alarms, essentially, and it'll look like activity is starting, but then nothing happens. Supposedly, unless gas got out somewhere and they weren't aware of it. Pyroclastic flow is one of those things that it happens fast, it happens violently. It's probably not going to surprise anyone further away, but if you're at the base of the volcano, good luck. So basically, also, the temperature ranges from like 1,000 degrees Fahrenheit to 1,500 degrees Fahrenheit. And for Celsius, that's 600 to 800. So it's basically one of the most lethal volcanic hazards because it incinerates or buries anything caught in its path. Pyroclastic flows are the ones that's the thing responsible for what happened to the people of Pompeii. You know what I mean? Just as a reference, that's what they were killed by for the most part. Like, not even the lava. The lava didn't do half as much damage as a pyroclastic flow did. So, slide 18 shows pyroclastic flow, scary looking thing right there. And then slide 19 shows the types of rocks that tend to be formed by pyroclastic flow once it does settle and solidify. It's just basically extensive sheets of rock that are called ignimbrites. The picture on the left is like a larger scale sample of ignimbrites. It just looks really rocky, jagged, with like a little weird glue of like earthy looking stuff. That's a pyroclastic flow. And then on the right, it's a smaller sample caught in like between layers of other types of rock, which means at some point there was an explosive volcanic eruption in that area, but then more rock kept building on top of it. So I'm assuming it might have only been like a single eruption. Who knows? Now, slide 20. And by the way, that's how that works, sedstrat, like sedimentation and stratigraphy, like that's what they're studying, is like the layers of rocks that build up that tell you something about geologic history. So yeah, if you're interested in something like that and being able to tell like what was going on in the environment, what rocks were settling, what that says about, like what was happening geologically there, you might want to look into becoming like, I think it's called like a sedimentologist, but I'm not sure, honestly. You might want to look into that. That was not really my specialty, and I was not the least bit interested in that, honestly. So yeah, slide 20 shows you a volcanic bomb. Basically, those are molten rock projectiles that are ejected violently by volcanic eruption. So again, usually a felsic thing. They're capable of landing kilometers away, like from the eruption site. So you don't even have to be close to the erupting volcano to be somehow bodied by a volcanic bomb. Just be aware of that. They can get quite big and are very, very hot. So they're another really bad volcanic hazard. Basically, felsic volcanoes are the absolute worst thing to have a house next to. Okay? If you want to live there for a long time and not have a horrible tragedy happen to you in your last moments, especially if it's an active volcano, do not live near a felsic volcano for your own good. So basically, it shows you a little, because they can vary in size too, like it says. It can be pretty big. That's a smaller volcanic bomb. And then on slide 21, you can see a pretty massive volcanic bomb, which again shows you why you need to be careful with these things. In slide 22, Mount Vesuvius is one of the, like, OG volcanoes that everyone has heard about because of what happened with Pompeii. And as you can see, they still have civilization pretty close to the volcanoes. Humans just don't learn. I'm sorry, but if I lived in a country where people were known to have died horrible, violent deaths at the base of a volcano that is still active, I don't know if I would rebuild right there. I don't know. Maybe I'm ignorant, who knows, but that doesn't seem safe to me, honestly. Now we're going on to slide 23. These are like shorter but still steeper coned volcanoes, basically built from small pieces of solid lava, which are like cinders. erupting from a single vent that usually only erupt once, quite violently though, and it can build into stratovolcanoes if eruptions happen repeatedly from the same vent. It says usually only erupt once. That doesn't mean they always do. And when they don't, they end up building stratovolcanoes again because of the explosive style of eruption. So basically, powerful blasts in these like specific volcanoes tend to like throw molten rock, ash, and gas up into the air. Obviously, the rocks cool quicker, so they fall back to the ground, breaking up into pieces that pile around the vent, hence the cinder cone. They can accumulate pretty high, like as high as like thousands of feet, like or 8,000 feet, that is. If the wind is actively blowing around the eruption site, I think this is just a thing for every volcano, cinder can be carried downwind and deposit there. So yeah, that's another type of volcano. That's like the third type. We've basically got shield, stratovolcano / composite volcano, and cinder cones. Now, the fourth one, wait, no, let me not get ahead of myself. Slide 24 is an example of a cinder cone. It's the Santa Clara volcano in Utah. It's one of 2 cinder cones in that volcanic field. There is another one. I just don't think they're close enough to be caught in the same photo because I wasn't able to get a photo like that. Anyway, now, like I said, now that we've actually arrived here, there's a fourth type of volcano that's actually just a type of eruption, and that's called the lava dome. So basically, lava domes are made up of lava that flow too thick to get away from the vent. So they flow so thick that it's like, and again, you will see this usually in felsic volcanoes. They basically flow so thick that they just can't even get away from the vent. So then that ends up creating lava domes. So basically, lava domes build via expansion from the inside. Magma continues to fill inside of the dome until some like kind of pressure as it keeps growing outward causes the harder like rock on the surface, like, you know, the one facing the elements, to like crack. And then as that falls away, little like there can be an opening that basically is created that allows all that hot like rock and gas to pour down the volcanic slope. This can happen unexpectedly when the volcano is not erupting. And that's, I think there, I read something about some hikers getting killed by something like this happening. So be careful. If you're ever hiking around a volcano that you think is not active, but there is a little dome of magma facing the area that you're going to be hiking, be careful, because you might not, I don't know if you would be able to see it coming. You know what I mean? And then, of course, slide 26 shows you an example of one of these guys. It's Mount St. Helens lava dome. So it does tend to like, oh, okay, so I didn't say this because I had it italicized. All right, so basically, lava domes can grow either on the flank of like massive composite volcanoes, so basically like around the side, like around any of the sides, or, and it's like the flank is basically like towards the ground, you know what I mean? Or it can grow in leftover craters. Remember how I said the volcanoes can actually collapse, like the opening can collapse and create craters? Well, something like a lava dome can grow in that crater and start causing more volcanic activity to come from that general area, even though it's not the original vent. So yeah, Mount St. Helens is an example of a lava dome in the crater of the once existent like active volcano. And also another note about lava volcanoes is that as lava squeezes out of the vent, because this is how it happens essentially, as lava kind of squeezes and bubbles and does its best to get out of that vent, it does accumulate as a giant pile over and around the vent that form all kinds of shapes. And like I said, at some point it will crack open. So it will crack open at some point. Don't think it never will. So yeah, obviously then we're moving on to the last topic, which is volcanoes and tectonics and, you know, all the stuff that has to do with that. So basically, volcanoes tend to crop up in certain areas more than in others. You very rarely see volcanoes away from tectonic plate boundaries, unless it's like a hot spot, which I will also explain. So basically, in divergent boundaries, which is just the crust pulling apart at the plate boundary, decompression melting creates like mafic magmas, usually leading to gently sloping volcanoes and new oceanic crust. Because this tends to happen more along like ocean floor. You know what I mean? So that's why like, you know, more mafic magmas tend to form, because it doesn't tend to be right below felsic composition rocks, so it doesn't become felsic enriched as it reaches the surface. It has very little surface to go through. So then it tends to be more mafic when it does erupt. And so you tend to have more shield volcanoes and like stuff like that underwater or close to the water. And also, lots of seafloor volcanism is an example of like divergent boundaries. You know what I mean? So yeah, and then of course there's the second type of tectonic boundary, which is or tectonic activity, which is convergent boundaries or subduction zones, as they can also be known. Because convergent boundaries, like ground pushing together, because that's essentially what it is two pieces, like two tectonic plates crashing into each other, that can create mountains or subduction zones. Sometimes both. Depending on the like where it is in the planet, you know. So basically, as water is squeezed out in these types of activities, it's like basically one plate is going under the other for subduction zones, and as it does that, water is squeezed out of the plate that's sinking, and that lowers the melting points of the rocks above the part of the plate boundary that, like the plate that is not sinking. Those rocks at the bottom start to get heated up, the melting point lowers, the magma starts rising again because it's less dense and keeps rising through more felsic rich continental crust, and that leads to felsic and intermediate volcanism at the surface. So basically, divergent boundaries, you see mafic volcanoes more often. Convergent boundaries, you see more felsic volcanoes. Then there's the wild card, which are the hot spots. So basically, as tectonic plates kind of shift over hotspots in the mantle, heat forms plumes of magma that essentially rise through the crust to produce volcanoes at the surface in places that you wouldn't otherwise expect, basically. Like, just in the middle of any plate, you can have a hotspot, and that has to do more with the mantle. So basically, explaining that, some areas of the mantle are hotter than others. So that tends to create certain hotspots as the tectonic plate moves over it, you know, does the whole thing where it's lowering the melting point, creating magma, magma's rising, reaching the surface. Since hotspots are stationary, sourced within the mantle rather than the plates, progressively older volcanoes can actually be tracked over the middle of tectonic plates to actually let you know how the plates have been moving over history. So for example, let's say that you have like a little line of volcanoes, you know what I mean? It just seemingly in the middle of nowhere. They're not at tectonic plate boundaries. You're just like, how did this happen? Well, that could tell you basically that there was a hot spot that's in this area. You know what I mean? Or rather, no, the hot spot in this case is in this little area, right? Once the tectonic plate was like this, and it keeps moving this way. So then, progressively younger volcanoes form closer to the hotspot, and that tells you something about the history because it tells you how the tectonic plate has been moving. Then there's slide 28 that shows you how hotspot volcanism works, just exactly what I explained. There's a hotspot in the mantle, rises up, creates volcanoes. As the plate moves away from it, those volcanoes are moving away, no longer have a source for the magma, so they become inactive. And then newer volcanoes keep forming along that line. So yeah, basically, that's all for today. I hope that wasn't unbearable. It was harder to get through than I thought. It's kind of, the problem is that my mind is racing and my mouth can't keep up. So I'm going to try to work on that for future videos. You can tell that I really like volcanoes because that happened a lot more for this video than for some of my others, I think, anyways. But yeah, at least I think so. So yeah, basically, I am going to do future video on tectonic activity for anyone who's interested. And basically, your only homework is to look up some cool volcanic eruption videos, as well as if you want to look into the devastating effects of past volcanoes. It's always fun to read about Pompeii, I guess. Sorry, people of Pompeii. What happened to you guys is perpetually intriguing to the people who came after. Such is the way of life. Hope to not be in such a catastrophic event that the only thing people remember about your death is how cool it was. I would feel really bad if that happens to you. So yeah, anyways, aside from all that, I hope you guys enjoyed yourselves and that you learned something, and maybe some of you guys got interested in volcanology. Who knows? Volcanoes are always going to be cool. You will never see me arguing with that statement. And for that, with that, I'm going to leave you guys because I have, other stuff to do. Turns out this is not a full-time job. This isn't even a part-time job. It's just a hobby. So yeah, hope you guys had a good time and hope you learned something, and stay curious and keep coming back.